Morning everyone. My name is Christian, and welcome back to another session in the series of AI Week. If you attended the previous sessions, you know that we've got sessions running each and every single day of this week, each on a different application of AI in a different industry, giving you a sort of a broad perspective on the various applications of that technology. Throughout the duration of this session, feel free to ask any questions, pop them either into the chat or the Q&A function. And that's about it for housekeeping. Today I'm joined by Klaus, who will be giving you a perspective of AI and the robotics in the nuclear waste disposal, if I got that correct. So Klaus, over to you.
Okay, well, thanks very much, Christian. So let me go and share my screen, and we can go and get started. So basically what I'd like to do with you today is to introduce you to the work that we're doing as part of the EPSRC National Center for Nuclear Robotics, which is all about using AI and robotics to deal with the challenges of nuclear applications and associated problems. So first of all, my kind of fabulous logo reveal for our laboratory. So I run the Embedded and Intelligent Systems Laboratory at the University of Essex, and this is kind of our recently adopted logo, just to go and share this particular piece with you. So let me go and talk to you briefly about what we're doing in the laboratory. So we're basically what we call embedded and intelligent systems. So embedded systems are systems that typically use some form of processor. So it's essentially any form of system that is more complex than a kettle, but isn't an actual dedicated computer. And our specific focus areas in these spaces is around making these type of systems more reliable and resilient. We're working in the space of robotics. So today I'm going to talk to you about both reliability and resilience and robotics. And we're focusing very often at applications in AI and computer vision. We're originally a hardware-based group that works on system on chip, and we've also do some work in cybersecurity and applications of embedded and intelligent systems in areas such as human rights. So the laboratory is predominantly working on UK research and innovation funded research. So we're one of the larger parts of the National Center for Nuclear Robotics, which is what I'm going to talk about today, which is a 14 million project from the Industrial Strategy Challenge Fund. That has also some additional leverage funding in there, and we work in other spaces around sensing in extreme environments, digital security by design, and the human rights and big data project that's based at the University of Essex. So that's kind of really one of our core elements of funding. We're very heavily focused on tier 1 funding, and just to go and give you a kind of a little overview what that kind of means in practice. So we've got our activity around resilient robotics and embedded systems for extreme environments such as space and nuclear environments. We're working also in the area of keyless cybersecurity with our startup Metrarch, and we have recently sold our other startup Ultrasoft Technologies, which has developed some technology that allows us to go and make a next generation electronic devices much better and reliable. So let's go and after this brief introduction, let's go and introduce you to the National Center for Nuclear Robotics. So I've got to start off with a kind of accessible explainer video. So hopefully the sound works. Christian, give me.
Hello, I'm a robot designed for the nuclear industry. I'm one of many devices developed by the National Center for Nuclear Robotics. The NCNR is a UK consortium of experts in robotics, artificial intelligence, sensors, radiation, and embedded systems. I don't have a voice or face when I'm at work, But hey, this is an explainer video. In the UK, we have nearly 5 million tonnes of legacy nuclear waste, dating back to the 1950s. Packaged up, this would fill Wembley Stadium. Using current technology, it's estimated that it could take up to 120 years and cost as much as £200 billion to clear it all up. That's why the UK has invested £42 million in the NCNR. Our goal is to reduce this burden on the taxpayer and make the environment safe for future generations. Robots like me can enter no-go zones where the levels of radiation are so high it's unsafe for humans. In other areas, humans can handle radioactive materials, but only for limited periods and by wearing special air-fed suits, which then become contaminated. 1 barrel of waste packaged by one human results in another 11 barrels of secondary waste, filled with contaminated suits. That's why they like to use us instead. We work longer shifts and reduce problematic secondary waste. To be really efficient, we need to develop a solid understanding of our surroundings. So the NCNR has experts in robotic perception, 3D modelling, artificial intelligence, and sensing and measuring technology. We're developing robots that can be deployed in hard-to-reach locations. These robots are resilient enough to access and assess disaster zones and fix complex nuclear waste problems that couldn't be solved before. The overriding mission is to make the process of nuclear decommissioning, maintenance of existing facilities and new builds safer, faster and cheaper. But investing in robots like me has benefits way beyond solving our nuclear legacy problems. Most likely, technology developed by our NCNR experts will be applied to areas as diverse as unmanned aerial vehicles, crop harvesting, and more efficient manufacturing, bringing economic benefits to the UK. The technology will also be helpful in other hazardous environments, such as space and underwater, as well as in home and social care. Areas where having a voice and face really does come in handy. If you want to find out more about how NCNR research is tackling our nuclear legacy and the potential it has to benefit our everyday lives, please take a look at the research themes on our website.
Okay, so that was our quick introduction to the National Centre for Nuclear Robotics. You can't got the core message basically. This is a really complex problem that's very, very dangerous for people to go and undertake, as you in some areas are totally inaccessible. In addition to that, we're kind of dealing with a situation where nuclear waste is, this is a diversity of different objects and materials, and that needs robotic capability that is actually very capable to go and deal with such complex issues. We know it's a massive problem, and robotics is really the kind of the prime way to solve that. But when we look at what's used in these spaces at the moment, we basically find that effectively hardly any robots are used in nuclear industry. Most of it's done by what we call robot manipulation that dates back to some sort of systems that were built in the 1940s. And even when they're using some sort of robots like this Brock hydraulic robot, you can see there, they're actually controlled by this chap out here that basically looks through a nearly 1.6 meter thick piece of glass to go and control his arm using some sort of joystick. So there isn't any real computer control in these spaces at present. Yeah. So this shows you kind of an experimental test rig that's built at by Sellafield at one of the National Nuclear Laboratory sites, and it shows basically how an operator controls these remote systems using a joystick. And that's basically a site which will process very large quantities of waste and has to sort that and package it into steel boxes for long-term storage. I mean, this uses basically joystick teleoperation with CCTV cameras. And the reason this doesn't look too bad is basically because the videos are massively sped up, basically, and as a result of that, this is a very, very slow and painstaking job where robots could go and make a real addition to go and solving this problem. I think the other real issue we have is that the operators of these systems are getting older, and basically there's limited new experts coming through at this point in time. So what we're doing in NCNR is we're looking at basically a set of user-defined examples that you can go and see here. They're basically this box encapsulation, which is sorting and placing waste into boxes. It's about characterization, understanding what's there, decommissioning something like a nuclear cell, and effectively looking both underwater or in the air to go and see what's happening in those spaces, basically. So for all of that to work effectively, we need systems that will be able to go and provide that capability effectively. And that's something which we're focusing at Essex, basically. We're basically looking at the effects radiation has on robotic systems. So if we move from these operator-based systems to robotic systems, we need to make sure that the robotic technology is actually capable to withstand these extreme environments. And you can go and see some of the experimentation we do with cameras here. So on the top left-hand side, you can see our setup to go and record these things. And the bottom right setup, you can go and see what a camera recording would be in such an environment when there is an active radiation source. And as you can see, there's a lot of radiation effects visible on the screen, and that's really something that's got a big consequence for using robotics, because a lot of traditional robotics algorithms for computer vision are based on having good quality images without much noisy overlays. So that's something where we're helping the overall consortium to find good ways of moving forward. In addition to that, long-term exposure to radiation can have some very severe consequences to the electronic that's deployed in these type of systems. And as a result of that, we need to go and not only understand how they would go and survive in these environments using the experimentation you've seen before, but we're also building effectively what we call radiation resilient embedded designs, where we use a combination of being able to go and assess what happens in the system together with some sophisticated methods to go and really build a system that can go and last as long as possible. So for some of these tasks, it's being able to go and even with partial functionality still deliver the overall mission is something that's really important. So this shows you some of the work we've done in the space of roll back and roll forward protection for embedded processor units as a way of dealing with such radiation effects. So that shows some of the work we're doing at Essex. I'll go and at the end of the presentation also introduce you to a couple of pieces of work we're doing around exploration and visual place recognition. But before we go into that space, I'd like to go and show you some of my colleagues' work at other universities that's contributing to the National Center of Nuclear Robotics. So this shows you some of the work we do around novel sensors and deployment systems. So you can go and see on the left-hand side novel optomechanic robotic sensors that are developed by my colleague Caspar Althofer at Queen Mary University, London, which are basically capable of operating in radioactive environments where purely electronic-based sensors would normally fail. On the right-hand side, you can go and see some new radiation sensors developed by my colleague Tom Scott at Bristol are deployed in things like pipe crawlers, flying and land-based robots that allow to go and sense radiation sources. And I'll show you some examples of where that's used in practical scenarios shortly. My colleague Rustam Stolkin at Birmingham University works particularly around robotic perception and learning. So that's all about being able to go and create 3D reconstruction of scenes where you can recognize the materials and objects, which would basically be a core element to go and help with this box encapsulation task where we're sorting through nuclear material to go and really find that. On the right hand side, you can go and see some state-of-the-art visual tracking algorithms that can allow to track manipulated objects and parts of robots in robot vision guided control. Mobility is not a core factor. Mobility is not a core factor for these type of systems. So what you can see here is some work done by my colleagues at the University of Edinburgh, Professor Mike Minstry, who is the leading expert on dynamics and control of walking robots and state-of-the-art cockpits. This worked very well a minute ago when I've tested it. So you're missing out on the walking robots. So these are essentially robots that are capable of traveling across terrain that's typically difficult to access for these type of systems. And what you can go and see up here is some of the sensors that we've seen earlier being deployed using a quadcopter to go and film nuclear waste grounds in Fukushima. So these have been employed both in Fukushima, Sellafield, and at other nuclear disaster sites such as Chernobyl to go and basically survey the ground. So this is a nuclear waste dump in Fukushima where basically the radioactive soil is stored in these sacks, and we use the sensor to identify when there's some radiation leakage. So you can see that the light areas down here are effectively radiation signs. Yeah. So show you some work around grasping and manipulation based on computer vision and machine learning, both from my colleagues at the University of Birmingham on the left, where they're working with Sellafield on these fuel rod retrieval tasks, and our colleagues at Lincoln University, Gerhard Neumann, and that shows you some of the work around being able to go and interact with flexible materials, such as this particular kind of bag that you can see here. So manipulation isn't just all about grasping. So this is basically the first autonomous robot developed by my colleagues in Birmingham that has been deployed in a radioactive environment, which is basically, this is the kind of laboratory set up here on the left, and this here is the actual deployment at a National Nuclear Laboratory, Preston, where the system is cutting a pipe in a nuclear environment. One of the other big things that you can see here that's beyond grasping is, for example, on the bottom left, the where we need to go and have some kind of force applied to contact. So this shows you an example where basically even with disturbance, a constant force can be applied to things. And this is another example of a tool interaction with a device. So that's going much beyond grasping towards real manipulation and interaction with these type of materials. Okay, so one of the other areas we're working on as part of NCNR is around manipulators. So you can go and see on the top left corner the hard manipulator that is effectively using a block-based system for grasping, cutting, grinding, and welding in nuclear spaces. And for some areas, these complex and large manipulators won't work because of the space constraints. So we need to go and have some devices that are suitable for working in very small areas. And you can see some of the some of the devices that are used in that kind of space, where we have soft robotic devices that can go and inflate on demand to go and manipulate these different elements. So you can go and, for example, see here a probe that can go and actuate both in length and also bend, and that has a camera in there as well, which would basically be something that can go and deal with these really constrained space situations. In addition to these kind of purely robot-based elements, we're also focusing around human-robot interfaces, where we're basically helping the operators to go and interact with the robots and guide the robots for a specific task. So you can go and see a number of examples here. So the top left, for example, shows a state-of-the-art haptic exoskeleton arm and hands that was developed with our colleagues at Birmingham as part of an EU project. And that basically allows the operator to feel objects encountered by the hand when they're operated. And on the right-hand top, you can see an augmented reality overlay laid on the human's perception, basically, where the AI plans to grasp an object, basically, and then the human acknowledges that this proposed grasp is safe and allows it to execute. In the bottom right, you can see some work that's done by our colleagues at Bristol Robotics using immersive telepresence. Okay, so you can see this interaction between human and AI-based robotics is something really, really important, and this collaborative element is something that I think becomes increasingly important in those areas where there is some high risk associated with it. So you can go and see examples here where we have basically AI and human collaborate to control a pair of robots, which is a gripper arm and the camera, undertaken by my colleagues at Birmingham and some collaborators. As well as on the right-hand side, you can go and see switching between the AI control and joystick teleoperations undertaken at Birmingham, that basically looks at ways of being able to go and provide the best possible operation. And that's basically a solution that will go and outperform both purely AI-based systems and purely based remote systems. So that's some very substantial contributions that NCNR has made in that space. Showing you some of the work we're doing at Essex around exploration, which is all about sending a robot into a kind of contaminated area and mapping this particular area. So there's some sites where it's not quite clear what's inside it, and due to the high level of radioactivity, there is actually a need for the robot to go and explore this area rapidly before it will fail. So it's all about building something that will work for such an environment by not only trying to go and provide the best possible coverage, but also doing that really as quickly as possible. So that's another piece of our work that we undertake at Essex, and that's particularly useful for exploration of those type of nuclear sites. So that's a quick overview of the kind of things we do as part of the National Centre for Nuclear Robotics. I have got, just as a closing piece, a video about some of the plays we do around visual place recognition. So visual place recognition is all about identifying where you are, but doing that without using something like a GPS or any other form of beacon. So basically we just have images of an environment, and we basically need to go and find out where we are in that picture. And as you can imagine, this is something that's very relevant for the applications we've seen, but also for things like self-driving vehicles and other things. So we basically use the fact that on those images of our environment, we can go and see some distinct features. So, if you can see Big Ben in the distance, you know that you're likely to be in London near the area of Westminster. But one of the big problems using these type of technologies is that depending on what time of the day it is, what time of the year it is, whether it's raining, dry, snowing, these places could go and look totally different. It's an area that's been developing over the last couple of decades, basically, and we're kind of moving forward in the technical development. We've got involved in visual place recognition over the last few years, basically, and have a very active research activity in there. As part of the National Centre for Nuclear Robotics, we're also collaborating with people such as the Australian Centre for Computer Vision in Brisbane, and a number of other collaborators worldwide to go and move the state of the art forward. So you can go and see a couple of examples of what we could call quite fairly kind of challenging environments that our technologies help to go and deal with, where traditional and more established algorithms weren't quite as capable. And we've taken some quite detailed work, and all of these pieces are published at kind of top computer vision conferences and journals. This is our kind of work around memorable maps as a way of dealing with visual place recognition, and we use that for practical applications in things like this little drone that you can go and see flying in our lab, as a way of helping to go and localize without using external GPS inputs, and that's something that's very, very useful for challenges in areas such as the ones we have in the nuclear environment, but also in places like underground or in potential kind of disaster scenarios where we may not go and have a suitable connection to a satellite-based system. So that's our brief introduction to the work we're doing as part of the National Centre for Nuclear Robotics, with some of the work we're doing here in Essex, and the work of our collaborators at 8 other universities in the UK, and a number of international collaborators. So thank you very much for joining me this morning, and I'm more than happy to answer any questions you may have at this particular point in time.
We'll see whether anyone has any questions. In the meantime, I've got a question quickly, just to give anyone else what I thought might have a question coming through. Yeah, so my question was actually related to the question that we received from the audience. So the question that we received from Karina, her question is, won't the robots become waste eventually too? And I had a very similar question, because if you have people obviously fixing their waste, and that their clothes or whatever become secondary waste disposal, won't the robots be classified as such as well?
Yeah, so yes, I mean that is correct. I think if you can't put it in context, though, at the moment, for every processed barrel of waste that's processed at Sellafield, there's about 9 barrels of new waste generated from the protective clothing that the people that do this at the moment wear. So I mean, it's not only very dangerous for these people, it's also generating an enormous amount of nuclear waste. Yeah, but one of the things we're doing with the work we do around characterization and testing of these electronic equipment is in fact very much relevant for that, because what we're trying to do is we're trying to extend the lifetime of these systems to go and provide a maximum mission lifetime. But yes, the robots will eventually also be affected by the radiation infected. There may be an element where we need to go and replace part of the robot. You can see with this exploration task I showed towards the end, one of the big elements around that is to go and send the robot into a nuclear environment without the robot returning to us at the end. So basically the robot will effectively perish in this environment. But what we want to do is we want to go and increase lifetime of the robot to a point where they can go and send us the maximum possible data back before they expire. But yes, the idea is very much to go and be in a situation where we can go and reduce the amount of waste that's generated using these type of robots that are moving forward. Yeah. So at the moment, the kind of the imaginary people you saw entering these radiation areas are basically kind of spending about 5 hours getting dressed before they go there, take an hour and a half to travel to site, then work at 1 to 2 hours processing the waste, and then take an hour and a half to get undressed and return to turn outside. So you can see that basically there is very little time that person actually spends undertaking the work, and that's really where robotic systems can play a big role in becoming much more efficient. And it's all, I mean, it's a very dangerous job in addition to that.
I've got a follow-up question, a very good question from Karina, so thank you for that. So how, a bit of a naive question, I suppose, how damaging is radiation to electronics? Wouldn't it be also useful to then salvage those robots that perish somewhere in those fields and then maybe reuse them?
Well, I think, so obviously this is in nuclear facilities themselves, so they wouldn't be, they would be in areas which aren't accessible to humans anyway. Yeah? So there is an element where once we build systems that survive for a much longer period, we can go and then recover these particular pieces as well. So I mean, it's part of the nuclear decontamination task is to go and collect kind of other waste and process it. Yeah. So we wouldn't really want to just abandon these elements there. There is a very varying level of radiation that we're dealing with. So some of those areas aren't very high radiation, and then it's kind of quite straightforward to go and protect these spaces and being able to go and retrieve the robot once it's done its work. And some of them are really, really high radiation, where basically the survivability is very, very low. Yeah.
So I've got another question. This one might include some trade secrets. So how can the chips and mechanics be best protected to ensure the longevity of the robots? That's again by Karina.
Okay. So one of the factors there is that in particular kind of electronics and the sensors are much more sensitive than the mechanical systems in themselves. So the mechanical systems are more straightforward to go and build in a way that go and has a much longer durability, but the electronic components and the sensors are potentially very much affected. So you can go and basically work with work in kind of two ways. One of them is shielding, so you go and basically use materials that will go and reduce the radiation effect to go and protect the kind of the inside of that. For example, the big glass window you saw at the beginning of the talk is a way of obviously shielding the operator from the radiation, and you can go and use similar materials for parts of the robot. You can go and use materials like lead and other things to an extent to go and reduce the radiation. It won't totally stop it, but you can reduce it in that way. And then obviously the other method to go and deal with the fact that we have radiation effects is by using redundancy in the system. So just like in space applications, you would have multiple components in the system would go and undertake the same functionality. And as a result of that, you'd be in a situation where you could go and accept a certain level of failure.
Interesting. I was going to say, what are the, again, a very simplistic question, but I suppose, I assume radiation isn't too damaging to more rigid, old-fashioned components in a way, like you wouldn't have something that is relatively solid state being damaged by radiation. So isn't there a benefit to making the equipment in a way slightly more old-fashioned, less electronic, less compact? Because I assume the newer chips that are smaller, have more transistors on them, are more susceptible to radiation sort of damaging, if that makes sense.
Yeah, I mean, a similar kind of approach as with space-based electronics is used in these type of systems as well. So we're kind of in a situation where the kind of technology you would use in such an application now was probably fairly old compared to what we see in consumer electronics. Yeah, so you're correct that basically, obviously, the smaller scale electronics we use, the more likely there is to be a significant effect. And it's all about balancing what level of functionality you want to achieve. Yeah, because I mean, if you think, yes, you can use the technology that's 10, 15 years old, but you remember what your mobile phone did 10 or 15 years ago, and compare that with what your mobile phone does now. So kind of there is an element where some of the benefits of modern microelectronics would obviously also be very useful to go and deal with these rather complex tasks. So that's very much where we are with the work we're doing in the National Centre for Nuclear Robotics to enable more modern functionality for these applications.
Okay, that's perfect. Thank you. I believe we've got no other questions. Any closing remarks from yourself, Klaus, at all?
Thanks very much for joining me this morning, and obviously it's good to see a number of you taking an interest in these pieces of work, and I hope you have fun with the rest of this week's sessions.
Yeah, awesome. Yeah. So just as a last point to everyone, so yeah, again, we've got more sessions just like this running throughout the rest of the week. So make sure you join us on that. And for today, thank you all. And yeah, we had a thank you from one of the members of our audience. Thank you so much for attending. And yeah, we'll see you in our next sessions. See you
Thanks very much. Bye.